Well, as the clock just chimed, I'm going to make a start. Good afternoon, everybody. I'm Edward Gomez. I'm going to be talking about robotic telescopes and world domination. And I'm an astronomer. So I'm an astronomer and I write Python a lot of the time. That's a part of my job that I enjoy a lot. Another part of my job that I enjoy a lot is talking to school kids and enthusing them about astronomy. I'm going to be mostly telling you about how I combine those two things, but I am an astronomer fundamentally, so I will be putting a little bit of astronomy research in there too. Now, I think there are 3 astronomers in the room. Put your hand up if you're an astronomer. And that includes if you've detected gravitational waves. Good. Yes, thank you. Right, okay, well that's good, because I've pitched my talk at people who are not astronomers. So, robotic telescopes to start with. This is a telescope. Back in 2005, Las Cumbres Observatory was founded, and we had 2 of these large telescopes. This is a beautiful telescope that's on the Hawaiian island of Maui, and it is primarily used for astronomical research. We bought this telescope with an endowment from Google. Las Cumbres Observatory was fortunately founded by Wayne Rosing, who used to work for Google. You probably don't know that name at all, but you're familiar with his Google child, which is Gmail. So that puts it in a little bit of context. When he retired from Google, he was given a lot of Google shares, and he's always been interested in astronomy, including making his own telescopes. And that includes grinding mirrors and putting them together. So he's a very switched-on person, and he wanted to. His idea was that you could combine telescopes with technology, and you wouldn't have to travel to exotic places like Hawaii. You could control these telescopes from anywhere in the world and do any sort of project, whether you're a professional astronomer or whether you're a school kid. And that's a very, very exciting prospect. People had sort of been doing that, but on a one telescope at a time type of thing. He wanted to build a global telescope network. So, what do we start with? Legacy code. So it's a very, very complex problem that you've got. You've got all these telescopes, or rather we started off with just 2 telescopes, because we thought we'll really understand this problem with 2 telescopes. So there was a company in Merseyside that was specialised in building these telescopes. And actually they went bankrupt just at the time that Wayne came along and said, I want to make telescopes, which is very fortunate because he bought that company for £1. Which is a bargain, really. I mean, we could have all done it, except the operating costs were £2 million a year. So not everybody could do that. But fortunately, they had all the expertise, and they produced 2 telescopes. But there was a lot of legacy code. And there was a lot of complicated stuff. So you had to interface a lot of hardware with a lot of other hardware, connect it to the internet, and then use software. And this was the sort of the software landscape that we had at the time. Who's heard of Groovy? Oh, a few people, great. I gave this talk to astronomers, and everybody thought I was taking the mick when I thought Groovy. Okay, so there's all this stuff, and people come and people go, software engineers come. Astronomers, like me, know a lot about this. I think Alice knows a lot about maybe Fortran 19, Fortran 77. And we'd also know quite a bit about this. And because it's telescopes, astronomers and software engineers have to sort of do this weird mind meld, this sort of crazy dance of astronomers sort of know what they want the telescopes to do and what they want the data to look like, but can't really articulate it very well. And the software engineers sort of understand code, but write things in a software engineer way. And so that's a very, very difficult thing to work together on. It presented a lot of different problems. And as various people left and various different expertise was lost, people wanted more features. And all of this stuff did that. All of the different software did various different things that nobody really understood because all of that knowledge has gone. We were in a massive era of technical debt. Now, we only had 2 telescopes at this point, and we were running them by, you had to install a piece of software on your computer in order to put observations onto the telescope. That doesn't really scale to a global scheme. So then fast forward 10 years, to full operations, version 1. So we built a whole load more telescopes. As well as these big telescopes that are the size of a double-decker bus, we have smaller ones, the size of family cars. We actually have 10 of those working in the field. We have very small ones, the size of a wheelie bin, or something called R2-D2. Are you aware how big that is? Okay. We have 9 of those. To sort of save on some site costs, we group them at very, very good astronomical sites. This is Siding Spring in Australia. So the big telescope is in this weird shaped clamshell, and the ones that are the size of a family car, the 1 metre ones, are in those 2 little pepper pots. And the 40 centimetre ones are actually inside the clamshell. So we group those in little clusters all over the globe. This is a beautiful picture of telescopes that you can't see because of the sun. These are all the places that we have telescopes. So we have 20 operating telescopes, and they form a global network. Now, to make that all work as a network nicely, we had to take a very, very brave step, and that was throwing away a lot of the code. A very brave step was taken to actually just use these 3 main, except in a few corner cases where we really couldn't get around it, but these 3 main areas. Java is used at the very lowest level operating system, hardware level, to talk, so that the camera can talk to a microcontroller. Python is used for everything else, and the user interface is HTML. So we still have all of this mess though. All of these things are physical hardware things. They're all still talking to each other. They're talking to each other much, much better now. But people don't want to interact with this. I mean, the world is here, but all these things, I don't care that there's a configuration DB that I have to set to particular things, and a telescope on the other side of the world might be in darkness, or it might be in daytime, or it might be cloudy, or somebody might be using it for something. I really just want a black box. That, Jen, is the internet. I just want a black box. I just want stuff. I just want a thing that I know how to use that's very, very simple. Well, obviously, there's a Python package for that. We created our own Python package to add things into the telescope queue. And so we had these 3 concepts. You had a block of time that you wanted your thing to happen. You had a molecule, which is an idea of the filters and the length of time that you wanted to look at a thing. And then the thing itself, where you want the telescope to point. Easy. You just import all of that, you construct your request, and there you go. There's your schedule. This is a nice Django admin interface. You can see all the date times over there. You can see which telescope, which site. Perfect. Not perfect. We have over 2,000 active users. And if everybody had this sort of Wild West approach of just saying, well, I want to use this telescope at this time, you'd end up with this all the time. People would jump on each other. There would be collisions non-stop. And not only that, this sometimes happens. Even though we've got fantastic astronomical sites that are at the top of mountains, above the majority of the cloud layer, it does occasionally snow. And that would be bad if everybody had to go, oh, it didn't happen, I now have to input all of my stuff all over again. Okay, you have a script, but you have to know how to do that. And that's just one telescope. If you've got 20 telescopes all over the globe, that's a really difficult problem that individuals have to know, right, my thing is only visible from that telescope, or that site and that site, but that site doesn't have any telescopes that I can use, and that site only has 1 telescope. It's a very, very complex problem. And really, machines are very good at doing this sorting out. So we needed an autonomous robotic scheduler. And I was thinking of a way that I could digest this very complex problem of all these competing priorities. And obviously Tetris is the easy way to do that. So you have your things that you want to observe. They're at different lengths, they have different constraints. And it's like a giant Tetris problem. We just need a piece of software to fit those together in the most efficient fashion possible so that it uses the network to its strengths, which is global coverage, and then we can be highly responsive. And so that's really, combined with all of those telescopes, we have Serral. Serral is with us today. CERL is on the front desk if you want to have a look at CERL later. So CERL stands for Scheduling Efficiently and Robotically on LCO. So we use CERL when we talk about Las Cumbres in schools. CERL is non-binary. CERL is not a he, and CERL is not a she. CERL identifies as it. If you want to know why particularly we do that, ask me afterwards. So, what was the goal for CERL? Well, CERL has to run continuously. CERL runs, and it takes 5 or 10 minutes for CERL to run, and that's because CERL creates a 2-week schedule for the entire telescope network. So that's 20 telescopes for a 2-week thing. It handles around 20,000 requests every time CERL decides to create a new schedule. And depending on the complexity of the requests, that's why it takes between 5 and 10 minutes. Occasionally, there's a massive blow-up and it takes 45 minutes. But we're working on how to make sure that that happens at the least number of times as possible. And it only happened in February this year, so that's good. CERL has to be good at multitasking. CERL also receives all of these different requests, all of these many varied constraints in Python. CERL is fluent in Python. CERL talks Python. But CERL is not written in Python. So that's, I'm sorry, this is a Python talk, but CERL is not written in Python, so that's a message. It's a very small bit right at the centre. It's a very difficult problem to solve this, and it has to be done very, very fast. So we actually use, we tried an open source problem solver, optimization thing, and now we use a Jorobi solver to deal with that. But it's just the very, very heart of CERL that does that. Everything else to do with CERL and the whole observatory is Python. So that was version 1, and that worked really, really well. It was a brave step to do, to throw away a lot of our code, but we had some severe limitations. That import LCOGT Pond, that was a nightmare to install. It meant that we had a huge number of dependencies. If we needed to move from one server to another, it took several days of downtime in order to do that. That's not ideal at all. We want to be fast, we want to be responsive to various different things. So, version 2.0, we very much needed stability in the network. And we did that with 3 main things. We wanted to be cloud-based. We didn't want to have a server that could catch fire in our headquarters, which is in California. We wanted to use microservices. Instead of having a Python package with lots of dependencies, we wanted to, our web portal used to take 30 seconds for the home page to load. That is not acceptable at all. And we wanted to know whether we were doing a good job, so we had to create operations metrics to find out whether the data quality was good. If you get crappy images, it doesn't matter if telescopes all over the world, you can dynamically reschedule. You've got crappy data. So we needed to find that. We needed to find where the bottlenecks were. And actually we use Elasticsearch and Kibana for figuring out where the bottlenecks are, and we can be incredibly responsive using those things. The being cloud-based thing was the very first step we moved towards stability. We used to have our entire archive on a machine, and that was a problem because we had to maintain that. We then outsourced that to an astronomy group just down the road from our headquarters in Pasadena, also in California. They wanted to charge us $300,000 a year to run that archive. We did a few calculations and we realized that we could do that for 5% of that cost if we did it in S3 on AWS. So we just did that. We took on we just said, right, okay, we've paid you a lot to develop this, but thanks, goodbye. Can we have all our data back? And they shipped it to us on disks. We shipped it to Amazon on disks, and now we pay $10,000 a year. $10,000 a year for our archive. We have 120,000 images each month added to the archive. We have 5.2 million individual astronomical images stored currently on our archive. It's a big S3 thing, and actually there's something, I think it's called Deep Freeze, or something like that anyway, where you can put long-term storage on S3, and it costs you even less. So we're actually paying less for that now than we were before, which is quite amazing. And it also means that we're very much more stable. We can put things from each of our sites into AWS very fast. We can put it from South Africa direct to AWS. We don't have to go through Pasadena. So South Africa has terrible internet, which is where one of our telescope sites is. Australia as well has terrible internet. But if you go direct to AWS, it's much, much faster. So again, we can be a lot more responsive. The microservices, we don't now have everything load on the homepage. We have our homepage as not a big Django project. It is a web page. We call everything through web services. And we make the documentation available. So if you don't like the observing portal, you can use our web services to make your own portal. You can make requests, so you can put things into Serral, and Serral will then put them onto whatever telescope and dynamically reschedule them according to your constraints using our APIs. You can check what the observatory status is. You can check the status of each of your requests, and you can download your data. So actually, what's I think it's a Yahoo phrase, we're eating our own dog food. We provided APIs as the very lowest level, and then we built on top of those APIs. And that made a huge improvement to our service. So actually, all you need now is you don't need to have this weird dependency-laden Python package that we developed. You can just use import requests, and you can do everything. And you can do this. You just need an auth token from here, and everyone in this room could do that. You can download astronomical data. So I'll just give you a little demo of how that works. Oh yes. So this is the homepage of our portal. The one thing that we desperately need is somebody with expertise in user experience, because I think this user experience is okay if you're an astronomer, but if you're a school kid, this is a terrible user experience. Oh, my little thing's gone orange. That means I have 5 minutes. So let's have a look. So all of these are requests submitted by people that I know, and the red ones failed for different reasons. Let's have a look at a green one which says completed. Let's look at that one. Hopefully I'm still on the Wi-Fi. Yes, okay. Again, user experience not great here. It says that there was 3 different observations, and let's have a look at, oh, and yes, of course, responsive design. There you go. Data, and there is our image there, and every part of this page was pulled in by an API. So when we clicked on that link, it made a call to an API and generated all of this. This is a link, all of this is populated from our archive, which is in S3, dynamically via an API. And the bit that I worked on is making these 3 black and white images into one color image. So I really hope this will now work. So generating color image. Ta-da! So that automatically combines 3 distinct images that were taken with a blue filter, a red filter, and a green filter, and combines them into a beautiful color image. Okay. Back to this. Oh, goodbye. What happened to you? So, our image data pipeline is Python, our data archiving is Python, our observing interface is Python, our science operations monitoring is Python. Python all the way down. And I wanted to highlight these in particular, are things that we use all the time. And Django, the Django community has been very, very supportive of everything that I've asked them. So they're a wonderful community, as are the Python community, but particularly Django was a bit of a mystery to me. So we have a variety of ways that we want to keep track of all of our telescope statuses. So this is our TELOps, not DevOps, TELOps, our telescope operations overview, and each block is one of those things that I showed you in that previous, on that web page. So each one of these things is a request that a user has made that Serral has put into a schedule. You can see that they're all nicely packed together because Serral does that sort of optimization beautifully. Purple means, I think, calibration, and yellow is daytime there. So you can see that we start off in Australia, go to South Africa, we go to the Canary Islands, then we go to Chile, and that's the Earth moving. These green ones are ones in the future, and these green ones here are ones in the past that were successful. You can see that these ones we hope will be successful, and these ones actually were, but those ones weren't. So that's a really useful view for our telescope operations people. But why do we do this? The reason that we do this is because we want great science to happen. I'm going to give you one example of some great science which happened, and the announcement of it was made last week, and there are two people in the room who were part of the other side of this. So, everybody's heard of gravitational waves, hopefully. Did anybody go to Duncan's talk yesterday about gravitational waves? A few of you, okay. Yep, Duncan himself is on it. So, you will have heard about this enormous effort to detect ripples in space-time by the LIGO Virgo teams. Now, these are ripples in space-time. This is a way of detecting astrophysical phenomena that we've never had before. But what I'm interested in is seeing light from those things. And for the very first time, back in August this year, we did see light from these gravitational waves. And then, what do? You have a big patch of sky that there is some light coming from. It was gamma rays, but we thought that there would be the type of light that our telescope sees, which is the same as the light that our eyes see. We call that optical light. So we wanted to learn more about this astrophysical thing by looking with our telescopes. So we pointed, this was the area of sky here, a 30-degree cucumber. So if you hold, I think somebody used this analogy of holding a cucumber at arm's length, that's the patch of sky that it would cover. That seems like quite a small search area. That's enormous. Like one of the little freckles on the cucumber is about the field of view, the size that each pointing of our telescope can see. So we looked at for galaxies in this, and our supernova team targeted galaxies in that area, and the fifth galaxy they looked at had this special event, which we now think is a kilonova. Two neutron stars spiraling in together produces a burst of gamma rays, and as those gamma rays fade, we see optical light. And this is the kilonova here. So this is the galaxy. There's two neutron stars. We're in that very distant galaxy, and then that shines as brightly as these things, which are stars in our own galaxy. So this thing here, this fuzzy thing and that dot, are something like 10 million light years away. And these things are a factor of 1,000 closer, and they're about as bright. So, we found that. We were not the first, we were the third or fourth, but that is a fantastic demonstration of our abilities because nobody lost data because they were bumped off the telescope. Serral dynamically rescheduled this. We didn't need to pull switches out and clear everybody out. Serral just said, this is a very important thing. I will shuffle everybody around in order to see this event. And my time is freaking out, so I am running low on time. And we followed it as the world turned with all of our different observatories in the southern hemisphere. No other observatory could do this. And this thing changed very quickly. If we could only see it once per day, which most observatories could, we'd have lost most of the information. We could see it 3 times per day from different observatory sites. Whoa! Spoiler. We also have, as of today, basically, we have 12 new education partners, one of which is going to be looking for gravitational waves. But all of them are going to be supporting education programs for school kids, for the next generation of scientists in the developing world, doing inspirational outreach events, all using our robotic telescopes. So I'm really looking forward to how that evolves. And finally, my badge is Ada Lovelace, which gives me an excellent excuse to talk about the Ada comic books, very briefly. I wanted to inspire kids with robotic telescopes, and I love comic books. So I worked with the artist Laura Sorvala to produce 3 comic books, the Ada comic books, and you can have a look at them there. They are free, and they're all about robotic telescopes. This one is about the discovery of the kilonova, but mostly they're about actually being anybody can do science, and empowering kids to believe that they can do science. Okay, I'm going to finish there and take some questions. Sorry if I took too long.
I'm not an astronomer, so this might be naive, but
it's okay.
Have you got a mechanism to see if someone asks for an observation that's already been made? You mentioned you had a huge archive. I just thought, is there anything that's...
Yeah, yes and no. So when you propose an observation, and well, I think the best way of doing this is with a demo. Okay, well, I don't know where my... Is that on a different screen? Okay, well, oh yes, that's it there. There we go. Right. So if I wanted to submit an observation, one of the things I specify is where I want to look. Sorry, conference Wi-Fi. One of the things is specifying where I want to look, either by a name or by a place in the sky. The system will say, when you type something in, yeah, here we go. It'll search those coordinates, and then it's probably doing that. You have that many frames already existing. Now, there might be a good reason you want to look at it again, because like the kilonova and Beauty and the Beast, there might be something there that wasn't there before. So you might want to get a sequence of images like that. Or you might just not know. So, yeah, we did. Thanks.
You showed an example of failed observations. What are the reasons an observation fails, and how is Cyril?
Oh, Cyril's gone face planted. It's very warm in here, that's why. So Cyril will detect whether something is totally impossible, and it will validate that request and tell you beforehand. So everything technically should be possible, that as long as it passes that validation. Then you get, because it's dynamically rescheduling, you might get your thing is very low priority, and high priority things come in and just bump you to the end. It might be that you have a very, very tight constraint, and so there is actually only one telescope that could ever fulfill that, because it's just in the right, your object is only visible for 20 minutes every day, and only at one site. And so that could be a reason that it fails. Thanks. Anybody else? Yeah, right at the back.
So you use Django for your front page, correct?
No, for this isn't Django, but the API is Django. So it's actually using, it's a Django website, but all that provides is an API to this, which is just HTML.
How did you do the asynchronous calls from Django to all the other microservices?
Say that again.
How did you do the async calls to the other microservices?
So it just happens over, so you have to have an authentication key, and that just passes that back and forth by JavaScript, and the JavaScript handles just calling all the different APIs. So I think the next talk is probably about to start, so thank you all very much, but you can talk to me out here until the conference ends.